the questions.
Hello, sir.
That will be helpful, sir.
Okay. And how was your quiz preparation?
Hello, sir.
Yeah, thanks. Yeah, hello.
Sir, activity 9.5 and tutorial 2, some doubts are there.
Activity 9.5 is it?
Yes, sir.
Is it okay? Is this the method of moments estimator thing, right?
Yeah, right.
Okay. Okay, then let us take that doubt and we will move to 9.6 lecture.
And tutorial 2, sir, some doubts.
Achha, you have doubt in the tutorial. Okay, what was the question number? Hello. Hello, Priyadarshini.
Tutorial 2, number 3.
Tutorial 2, question number 3.
Yeah. And activity 9.
And activity 9. Okay, your voice is breaking or are you not speaking up? Is my internet connection?
No, maybe it's a fault in my mic only. Activity 9.5, sir. 2, 4, and 5.
2, 4 and 5.
Yeah.
Okay. Do any of the people other than Priyadarshini have the same doubt? No one? Okay, let me re-ask my question. Reframe my question. How many of you have done activity 9.5 questions? Hey,
So I've done it, but my doubt is in fourth 9.5.
9.5, question number 4.
Yeah.
Okay. And Baki people? No one did 9.5 yet, is it?
Yeah, I need, sir.
Sir, this 9 activity, like week 9 could be given after the quiz, sir. It's really difficult because 5, 6, 7, 8 itself, they are difficult. So, I mean, it's we need to practice.
Yes, sir, because I'm having so many doubts, but then I thought I'll again try to
So, why
solve
it's
them
given
and
on
then
6,
get back.
Why?
Why it's been like the submission date is 6, sir. At least it could be given after quiz 2.
See,
Would have got some
yeah,
time.
we do understand your problem, but you also should understand our problem. See, if we postpone this to 9 or somewhere around after quiz 2, when was your end term?
7th
7?
August
7th, right? So if your deadline of week 9 itself got postponed to some 9th or 10th, when will be the deadline of 10th or the 11th and the 12th week? And when will we calculate the eligibility for your exam, and when we should be giving you the hall ticket and everything? See, there are lots and lots of things happening behind which we don't know, right? The same thing happened in the previous term also. This was already I have explained it. If it has at least 1% of chance of postponing the deadline, we could have done it without you people ask. Okay.
Stats 2 is not that easy, sir. It's
Yeah.
we are facing the difficulty. I mean, what is
Correct.
the difficulty? We already know that.
Correct.
So, we as working professionals, we have other commitments also, sir. It's not like entire day we are sitting with stats 2. Yes, we of course give at least, I try to give 2 to 3 hours time in a day. But still, the doubts are not getting clear, sir. We are not able to solve all the questions on our own. I mean, we need help, like open sessions
Okay.
and solve it us.
Yeah, we are there, right? Here you can ask whatever doubt you have. Okay, I won't sleep till everyone's doubt got cleared. Okay.
Sir, but
Sir.
that is the thing, sir. How many of them are solving week 9? Because they are all
Acha,
busy with preparing
week
quiz
5 to
2,
8.
sir.
Yeah, correct.
Sir, I have doubts, sir. Sir,
Doubt of
week 9, sir.
yeah, we will talk about doubts and everything. Okay, I
Yeah.
will take it. Okay.
Okay, sir.
What am I asking is how many of you have actually done AQ 9.5?
I
And
have done,
among
sir.
those who have done 9.5, any doubts in those particular 5 questions?
Yeah, yes, sir. I have doubt in question number 5.
5.
Yeah.
Now doubt in question number 5. Someone raised a doubt in question number 4.
Yes, sir.
And Priyadarshini, what questions have you asked me?
2, 4, and 5.
2, 4, and 5. Okay. So again, this question is for only people who have solved AQ 9.5. Okay.
Yes.
So you have done question number 1 without any
Yeah, I
trouble.
just could do it. I could
Yes.
do it.
Yes, sir.
Everyone can do that. They have
1
given
and
6.
3, I could do it.
Okay, 1 and 3. 1 and 3, you people can do it.
Yes, sir.
So if you can do 3, that means you know how to find how to estimate the parameter using method of moment.
Yeah.
Can I say that? So those who have done AQ 9.5.
Yes, sir.
Yes, sir.
Okay, if it is geometric or if it is Poisson or if it is something else, whether it is discrete or continuous, whatever the distribution is, if you don't know the parameter and you know that the parameter is a constant value, and I have given you a sampling or the sample and sample, now you know how to estimate the P using method of moments. I'm not going to explain this. That is why I'm asking this question. You know how to approach a question using method of moments. How to estimate a parameter using method of moments.
Yes, sir.
Yes, sir.
Okay. Okay. Let me share my screen. I haven't shared my screen, right? Just a second. And the people who haven't done 9.5 yet, just take some time or breathe in between. Just hold. We will come to lecture 9.6 and we will discuss. Okay. Okay. Is my screen visible now?
Yes, sir.
Okay. So we are good with question number 1. We will deal how to solve question number 2 in AQ 9.5. Okay. So it is given that the density function of a continuous random variable is given by. So we have been given you the density function. So when we say density function, we know that x is continuous random variable. Correct? Probability density function. Okay, it is given continuous also. No need to worry. So continuous random variable given by fx of x is equals to 1 plus theta x by 2. And also we have the support given to us from 1 to some minus 1 to 1. Now that we have the density function with us, what we asked you is let x1, x2, xn be IID samples of x. Find the estimator of theta using method of moments. Okay. So you only answered me how to estimate a parameter using method of moments, you know. Now just quickly tell me what are the steps, main steps. What is step 1? What is step 2? And what is step 3? Final step.
M1 equal to expectation of x. So
Okay.
expectation of x is you have to get
fx, yeah.
So expectation of x is equals to m1.
Yeah.
Okay. That means this is the first moment.
Right.
correct? As we have only one parameter, it is sufficient to have only one moment,
Yeah.
Yes, sir.
correct?
Yes, sir.
So that particular first moment is actually the expected value of this random variable x, which is e of x. So e
Right.
of x we will equate to m1.
Yeah.
And what next?
Then you have to calculate that expectation of x, equate it to m1, and then find out the value of theta. Yeah, parameter.
Correct.
Yeah.
Now what will be the final?
Then instead of m1, small m1, you have to take capital M1 and
Yes. Replace
substitute.
theta
Yeah.
with something like theta hat me, and also replace small m1 with capital M.
Yes.
And whatever the x are there, that means small m1 with capital M1 means whatever the small x are there, replace it with capital. Correct?
Yes, sir.
Yes, sir.
Now the first point is we need to find the expected value of this x. How do we get
Yeah.
expected value of this x? From the distribution function, from the density function we know. So this we know.
Yes,
Yeah.
sir. We will integrate, sir.
So as
Integrate
fx, sir, we'll
x
integrate.
into fx.
Yeah.
X into fx.
Correct.
Yeah.
So
Yeah.
we
Minus
have an
one.
expected value of x
Yeah.
is integral x times
fx
fx of x dx.
Yeah. Yes, sir.
And the integration is within the support of x.
Support.
Yeah.
Correct. So the support is -1 to 1.
Yes, sir.
And this x will be x itself. And fx of x, it is given that 1 plus theta x by 2. Correct? Dx. So from here we will get the expected value of x. So how do we do that? If you know small basic integration formulas, you can do it.
Yes, sir.
So this is
So-
like x plus theta x square by 2 dx. Correct? So
Yes, sir.
if we integrate this thing, so x and x, we know this, right? Integral x to the power n dx will be x to the
N plus
power n
1
plus
upon
1 upon n plus 1.
n plus 1.
Yeah.
So the same thing here. So this is x to the power 1 and this will be like x square by 2
Into 2.
plus theta. This is now n is 2 here. So 2 plus 1, 3 by 3 divided by 2. Okay, the limits are 1 and -1. Okay, so I'm not doing new thing. Okay, this is all we studied. So the small integration thing.
Can't we load the 1 by 2 outside, sir?
Okay, what?
Can't we load the 1 by 2 outside?
You can pull out 1 by
Yeah.
2 outside. It doesn't change. You pull out 1 by 2. So anything. This is also same thing. Okay. So just substitute 1 here. We will get 1 by 2 plus theta times 1 by 3 divided by 2 minus. Now substitute -1. So -1 whole square by 2 plus theta into -1 whole cube by 3 divided by 2. Correct? So this will be half plus theta by 3 minus half plus theta by 3 divided by 2. This will get cancel and this will be like whole will be theta by 3. Correct? Theta by 3 plus theta by 3, it will be 2 theta by 3 divided
Yes,
by
sir.
2. 2 and 2 will get cancelled and it will be theta by 3. So this is just simplification. Okay. Now what we got is our expected value of x as theta by 3. Now we know the expected value. Now let's go to the step 1. So what we have to do, our expected value should be equated to m1,
M1.
small m1. So expected value of x is theta by 3. So theta by 3, I will equate it to m1. Next thing is we find the parameter which is theta in terms of m1. So this will be 3m1. Okay.
Yes, sir.
So theta is 3m1. That means
Yeah,
this will be 3m1. So m1 is
one is x1 plus x2 till xn upon n.
correct.
Multiplied
So
by
this will be multiplied by 3. So this is 3 times of x1 plus x2 plus xn divided by n. So this will be the method of moments estimator. Did we do anything new apart from what we know? So these are the 3 main steps, right?
yes, sir.
So actually for me these basics are like perfect, but the thing is when I try to apply, like in case of question 4, I somehow do some mistakes
Okay,
or something.
we will do that question 4 also. Okay.
Yeah.
Okay. Now Priyadarshini, is your question number 2 clear?
Yes, sir.
Yes.
Yes, sir.
So yeah. So option B will be the correct answer. Okay. Now let us see question number 4. So question number 4 is a die is such that the probability of getting any number from 1 to 5 is theta. Okay. So now we will try to solve question number 4. See, we actually we need only one step. Okay. So whatever the question is, whatever we know and what the question is, between one step is understanding. If you understand the question properly, you can do it. So baki sab cheez we know how to do, what to do, everything we know. But what we are missing here is understanding of the question.
Right.
So that you will get by practicing. Okay. So
Sir,
here what
in
it
this,
says,
sir,
yeah.
in this question case, actually 6 is also there, so it will be 0, no, sir. Otherwise 0, you want to say in this.
No. See, if you have a die, okay, if you throw a die from 1 to 6, any number is possible. I'm guaranteed that among all the 6 numbers, any number will come with probability 1, right? It won't struck with corner basing the ground, and it won't be like in improper shape, right? Any of the face is visible. Am I right? If you throw a
Right.
dice, yeah, I
For a
can
fair
say
die. Yeah. For
for
a
a
fair die.
fair die, I can say with probability 1, the face, the number that is shown on the die will be in between 1 to 6. Correct?
Mhm.
That's okay, sir. But when it is asked 1 to 5 is theta means what?
1 to 5, if 1 to 5, each of the value is theta. So it is given that a die is such that the probability of getting any number from 1 to 5 is theta. So what it says is, so between 1, 2, 3, 4, 5, there is a probability that either 1 or 2 or 3 or 4 or 5 appears when you throw a die is theta. That means the probability that if you the probability that 6 appears on the die will be,
1 minus
Otherwise 0,
theta.
right, sir?
no, it's not 0.
1 minus theta,
1
no?
minus of this event, right?
Okay. All right, sir.
So see, 1, 2, 3, 4, 5, 6 can appear on the dice. The probability that either 1 or 2 or 3 or 4 or 5 appears is theta. So what is the probability that, so this is the complement, right? What is the
1
probability that,
minus 5
One.
theta.
Yeah,
yeah,
one.
this is 1 minus theta. Okay, so see, this is what we are missing actually. So if you understand, now if you understand this, it is said that the die is rolled 10 times and the outcomes are 1, 6, 5, 5, 4, 6, 6, 2, 3, 4. Now actually we have a sampling here. Sampling of 10 sampling. One particular sampling we have. Now what we have to find is find the estimate of theta using method of moments. So we have to estimate theta. Theta is actually the probability. So we have to estimate the probability given one sample to us, which is 1655 46 6234. Okay, this is one sample given to us. So the same way, right? If you have given some x1 to xn,
Theta minus 1,
now
theta,
n is here 10. So we have given you 10 samples, 10 times the die is rolled. Now what we have to find? We have to estimate this parameter, right? For that,
Yeah.
the same approach. Step 1 is you have to find the expected value of x.
Right. Yeah.
So what is the expected value of x?
So I did it theta by phi into 1 plus theta by phi into 2 up to theta by phi into 5 plus 1 minus theta into 6. Is that right, sir?
Theta by?
Theta by 5 into 1.
No, it's not theta by 5, right? Is it?
Because, sir, up to 1 to 5, it is theta. So for every like for 1, it will be theta by 5. For 2, it will be theta by 5, right? So for calculating E of x, I have to use the value 1, 2, 3, 4, 5 multiplied by the probability.
Right.
Right, no?
Mm-hmm. Correct. So expected value is summation I is equals to 1 to
1 to
6.
5. 1 to 5, na, sir? Because 6 ka, it should be 1 minus theta. So 1 to 5, theta into whatever value.
Yeah. We have six values, right? I'm just writing the formula of expected value.
Okay.
So probability that x takes x. So this is the expected value when it is discrete. So previous
Right.
case is continuous. This case is discrete. So this is 1 times probability that x takes value 1 is
Theta by 5.
theta by 5 plus 2 times theta by 5 plus 3 times theta by 5 and 4 times theta by 5 plus 5 times theta by 5
Plus 6
plus
into
plus 6 into
theta,
1 minus theta.
Yeah.
Right, this
That
will be the
as well.
expected value of x.
Right.
Now if you simplify this, we get
In the last term, by 1 we can write now, sir, to reduce the confusion.
by 1 you can write. Okay, now it is like 1 plus 2 plus 3 plus 4 plus 5 divided by 5 into theta.
Yeah.
Correct, plus 6 times
1 minus theta.
1 minus theta. So this is actually 15
by 5.
If you submit 15 by 5, it will be 3. So this will be 3 theta plus 6 minus 6 theta. So we will get 6 minus 3 theta. So now we got expected value of x in terms of theta.
Yeah.
Now our step 1. Let's go to the step 1. So this 6 minus 3 theta should be equated to m1.
Right.
Now from here we need to find theta. So theta will be 6 minus m1 by 3.
Yeah.
Correct?
Yeah.
Now what is m1? Now what is step 2? Step 3. So this theta hat mme will be equal to 6 minus m1 is x1 plus x2 plus and so on xn by n divided by 3.
Yeah.
Here we have directly given you the samples. We have given you 10 samples. That means n is equals to 10. And also each x1, x2, xn is also given to us. Right? Those are nothing but, this x1 is nothing but 1. x2 is 6. x3 is 5. x4 is 5. x5 is 4. So what we have to do is 6 minus, just substitute those. 1 plus 5, whatever are there. So whatever these things, 1 plus 6 plus.
Looks like I did some mathematical mistake because otherwise the steps are right.
Steps are right. Let us check.
Yeah.
So this will be 1 plus 6 plus 5. So 7, 10, 12, 12. How much? 12, 17, 21, 27, 33, 35 plus 7. 42. I'm getting 42.
Yeah.
Just cross check. Okay. And n is 10 by 3. This will be like 6 minus 4.2 divided by 3. And this is somewhere around 1.8 by 3. And this will be 0.6. What is the answer given?
0.10.
Yeah, I also got 0.6, but the answer is
Okay. Okay. I think even I mistook. See, this can be read in two ways. A die is such that the probability of getting any number from 1 to 5 is theta means, okay, in this question, I guess their intention is
Each
each
number
number,
gets
yeah,
theta.
theta.
oh, okay. Oh, I see. Okay.
Okay. So if each number is getting theta, then getting 6 will be 1 minus 5 theta.
Yeah,
Right.
right. Okay. So if we do that, I think it will. Okay, fine.
If we do this, we will get it
Okay, okay.
correctly. So
So
this will
my
be
worry
theta.
was I have not understood how to go about it. So that's what my
Okay.
worry was. Now, if it is that thing, then I'll do this. Okay. Thank you,
So
sir.
this will be like 1 minus 5 theta. And this will be like 15 theta. This is 15 theta. And this is 6 times 1 minus 5 theta. So 6 minus 30 theta. This will be 6 minus 30 theta. 6 minus 15 theta.
15 theta. 15.
Yeah, 15 theta. So this is 15 theta. And from here we will get 6 minus 6 minus m1 by 15.
15.
So this will be the chain. This will be 15. This will be 15. And therefore this will be 1.8 by 15. And I guess this will be correct.
Yes,
This will be
correct.
something like correct. This will be like 0 0.0.
0.12. 0.12.
0.12, correct. Exactly 0.1. Yeah, this will match, I guess.
Okay, sir. Thanks.
Yeah.
Calculate.
And yeah, even okay.
May I ask a question regarding the previous problem?
Previous one, is it?
Yeah, the previous one that you solved.
One second, sir. What is the twist over here in this question?
What is?
The twist where we went wrong actually. I'm reading the question wrong.
Where we went wrong actually is what we thought is among this any number, I thought either getting 1, 2, 3, 4, 5, any of getting these numbers, I thought with probability theta.
That's
But the
correct,
question
sir.
no, but the question says is any of the number, getting any of the number, like getting 1 or getting 2 or getting 3 or getting 4 or getting 5, each of them has probability theta.
That's okay, sir. But we are get the thing which is less than 6 means 1 to 5 times.
No. It's not
So
lesser than 6. It's actually, they are saying
probability
that
of 6 should be deleted. That's all. The concept is like that.
No, not like that. So the concept is, they said from 1 to 5, probability of getting each of the number has probability theta. So in order to get 1 on the dice, it has probability theta. So for 2, it has theta, 3, it has theta, 4, it has theta, 5, it has theta. So these 5 values, getting 5 values, it is uniform. It has equal probabilities with theta. So among if it has equal probabilities theta, then 6 will have. So x is a random variable. It can only take values 1, 2, 3, 4, 5, 6. Now one takes with probability theta, 2 with probability theta, 3 with probability theta. So what is the probability that the random variable x takes value 6?
Okay, now I understood, sir. Thank you.
Correct. So this will be 1 minus 5 theta. So earlier we thought getting these all numbers is theta, and for this is 1 minus theta. So that is where we went wrong.
Thank you, sir.
Okay. Yeah. Yeah. What is the doubt in previous question?
The previous question, okay, till the theta hat MME, that one is clear, but how did it convert into x square? The option D is x1 square plus x2 square plus x3 till xn square. So how did that convert?
Correct option is option B, right?
Option B, is it? Okay, sorry, that was the misunderstanding.
Yeah, correct
That was
option
my
is
misunderstanding. Yeah.
okay. Okay, 2, 4 is okay. Now can you try fifth one? Or shall I have to do
Sir.
it again?
Yes,
Now
sir.
will you guys try?
Yes, sir. I have done it, sir. Can
You
I
have
tell
done
you?
it?
Yeah.
No. If you tell me, it's not about telling me. I'm just if you guys understand how to solve question number 2, question number 4. Now here we have 2 parameters. No, we have only 1 parameter, right? So what is the difference now? Okay, can you guys try Priyadarshini or Kavita?
I couldn't understand actually, so because there are two things given. All this while we were doing it with one, right? So whatever we are getting, we are used to substitute it and get it. But here, when we are given two things.
No. We have given you the probability that x takes value 1 is with probability it's some 2 times of 1 minus p by 2 minus p. And
Okay.
probability
second is
that x
equal to
takes
1.
value 2 is p by 2 minus p. So just try to add those two. What will you get?
Okay.
1.
So you will get 1. So that means x can only take values
Like
1 and 2.
1 and 2, yeah. Okay.
Yeah. So it's like x is a random variable with which it
So
takes
we can
1 and
calculate
2.
e of x based on that. Okay,
Yeah,
got
e
it.
of x is
Yeah,
you calculate e of x, just equate it to m1. From there
now
you
understood.
in terms
Yeah.
of m1 and then replace it.
Right, got it.
Okay.
Thanks.
Okay. Is it okay for Priyadarshini and who is the other guy he asked? Okay. Okay, let's come to 9.6 now. Okay, we will come to problems. Okay, we will come to problems. Before that, we will discuss few topics and we will come to the problems. So yeah, so in the last lecture or the last live session, we have discussed this method of moments estimator. So how do we estimate a parameter using method of moments thing? So there is another method which is called maximum likelihood estimator. So this is another method to estimate the parameter. Not another method. This is a different kind of estimator, which may sometime is equal to the method of moments estimator, but sometimes it is different from method of moments estimator. In some cases, method of moments estimator is easy to compute, but in very few cases or very special cases, maximum likelihood estimator is the best way to compute. So that is why we have two different methods to compute or to estimate a parameter. So sometimes we may not get the we may not get the answers via method of moments estimator, or it will be too complicated to compute from there to estimate a parameter. Then in that cases, this particular maximum likelihood estimator will come in handy. Okay, what is this maximum likelihood estimator? Just like method of moment estimator, there is a way or there is a standard steps we follow in order to find the maximum likelihood estimator. So the same setup, we have some x1, x2, xn. There are n samples which are IID x, and this particular x has parameters theta 1, theta 2, and so on. We don't know how many parameters x can have. As of now, we studied only maximum of 2 parameters. correct? So for Bernoulli,
E, one parameter.
we have one parameter which is P. Same like Poisson,
Lambda exponential.
one parameter which is lambda, and also exponential is also lambda, which we have one parameter. And what else we have as a one parameter?
Normal parameter.
Geometry.
Yeah, geometric P, we have one parameter. So these are some examples of distribution which has only one parameter, and we have also studied examples of two parameters. So just like binomial,
NP.
normal,
Sigma square.
sometimes
Gamma.
uniform
Gamma.
also. Huh?
Gamma also.
Yeah, gamma, uniform AB, gamma, alpha, beta,
Then
normal.
beta distribution.
Huh?
Beta distribution.
Beta we have, and we can have log normal.
AB. Log normal we have not studied.
We didn't study about it.
No.
Okay. Binomial and P. So these all have two parameters. Yeah, just now we have seen these distributions only. So parameters will be like theta 1, theta 2, or theta 1, only theta 1. So one parameter or two parameters, not more than that in our course.
So are there distributions with more than two parameters?
There will be distributions with more than two parameters also. See, simple case, you see, in the lecture also it is explained, right? We don't know, we define distributions which takes values 1, 2, 3 with parameter P1, P2, P2.
Okay, in that way.
Okay, this has three parameters.
But this is not uniform?
That is not uniform. See, uniform, what is uniform?
No, discrete uniform. I said discrete.
No, even discrete uniform. See, if you say discrete uniform, that means whatever the value the random variable takes has equal chance.
Yes.
Here, it doesn't have the equal chance.
Got it.
Okay.
But
Just
in
like
such
scoring score by a batsman, batsman scored on a particular ball is not uniform. So probability of getting 6 is very, very low, than getting 4, then 3 runs is very difficult, 2, 1, and dot ball has more chances if it is a test cricket. Okay, so they have different probabilities. So there you have 6 parameters. Okay. So okay, it's an out of syllabus kind of thing if you wanted to discuss.
Yes.
So let's put it aside.
Let us proceed.
Yeah, let us proceed ahead, and we can discuss it by the end of the session if required.
in such cases, are we getting all these ones into normal kind of thing or some other method?
Are we getting?
Yeah, all the probabilities, are we getting it to normal kind of thing or some other method we apply? You explain just one case kind of thing. Getting a 0, 1 kind. 6 runs and all.
Can you reframe your question? I can't understand what you said.
Yeah, you have just explained, sir. In
Yeah.
such different cases kind of thing, are we getting all these samples into normal distribution or some other method we need to apply, sir?
Where come this normal came into the picture? Like, we are not using any normal thing, right?
Right, sir. Please continue. I'll ask the
Yeah. If that is not the thing I explained. That is a different distribution. So it has 6 parameters.
I would have confused it.
Yeah. So okay, let's come back. So these parameters we know, right? These parameters are either 1 or 2 in this particular course. These are the parameters X has, and all these X1 to Xn are IID samples of X. Now, the likelihood of one particular sampling. So if you take one instance of this samples, which is denoted as small x1, small x2, and so on xn. So this likelihood function is denoted as L of x1, x2, and so on xn. Okay, this is the denotion of a likelihood function, and it is defined as product of, okay, product of the density functions of each of the x's. So that means this is actually the product of fx of x1 times fx of x2 times fx of x3 and so on times fx of xn. So product of the distribution function, probability distribution function. So if it will be density function if the given, if we take x as continuous random variable, it will be PMF if it is discrete. So this will be the product of PMF for discrete case. It will be the product of PDFs for continuous case. So this is the likelihood function. So let me take one example here. If I have something like x follows binomial 2 comma half. Okay. So what this mean? So what are the values x can take?
Zero, 1, 2.
Correct, at least one. So 0 with probability 2c0 half power 2, 1 with 2c1 half power 2, 2 with probability 2c2 half power 2. Correct, this is what binomial. So if I have taken one sampling out of this, like let's say 1 0 1 1 2 0 1 2 3 4 5 6, okay, 6 samples we are looking at. So L of, so this particular L of 1 comma 0 comma 1 comma 1 comma 2 comma 0 is given as so we shouldn't take like that. So if I say half directly, so that is where you are confused. So what we will compute if I have given you the probability directly, what we are estimating then?
Yeah, yes, sir.
So this is P. So this will be half power 2 minus P, half power P, half power 2 minus P. Is it a bit confusing? Shall we go with Bernoulli?
No, sir. You can continue. You can.
Simple
So, sir, let us
Bernoulli
continue by the way, sir.
by this. So why I am not taking Bernoulli is because in lecture
Yes,
professor has
enough examples have been taken on the
yeah, so Bernoulli you understand it easily. Okay, if you are confused, just go there, watch the Bernoulli case, and you will understand this. So this will be half power.
Sir, why are you taking
So,
half, sir? Why
yeah,
are you taking
exactly.
half?
It should be P raised to
sorry,
something, na, sir?
Yeah, yeah.
I was
Yes,
actually
sir.
thinking, I thought I
Correct,
missed
correct.
something. So,
Yeah.
okay.
Thanks.
Okay.
So this is 2c0 into 1 minus P whole square. So this with probability 2c1 into P times 1 minus P, and this with 2c2 P to the square. Correct? This is correct.
Yes, sir. Right.
So 2c0, in order to remove more confusions, let us take the values. This will be twice.
So I didn't get how you got P square at last term.
P square is like, see, it is like 2c2 times P to the power 2 times 1 minus P to the power 2 minus 2. Right? What is fx of this? Fx of x. So this is 2cx into P to the power x times 1 minus P to the power 2 minus x. Correct? This will be the PMF.
For
Correct,
this
right?
particular example.
Yes.
For this particular example, fx of x is 2cx times P to the power x times 1 minus P to the power 2 minus x. So x is x, you take values 0, 1, 2. So if you take 0, this is 2c0 p to the power 0, 1 minus p whole square. So this is the probability that x takes value 0. So that will be 1 minus p whole square. Similarly for 2 also, you take probability that x takes value 2. So that means small x is 2, fx of 2. So that will be 2c2 times p square times 1 minus p whole to the power 2 minus 2. So this will be 1. Therefore, it will be p square.
Okay.
Okay. Yeah. So this is 2 times p times 1 minus 2. So this L of 1, 0, 1, 1, 2, 0 will be the product of fx of 1 times fx of 0 times fx of 1 times fx of 1 times fx of 2 times fx of 0. So fx of 1 is 2 times p times 1 minus p. So fx of 0 is 1 minus p whole square. Again fx of 1, fx of 1. So this will be square. So I have fx of 1 3 times. So this I can make it cube. Yes or no?
Yes.
Yes,
I
sir.
can make it cube directly. So there are 3 terms in my product which are same fx of 1. So I will cube it. It is actually fx of 1 whole cube. And also I have 2 terms fx of 0. So I can square this. And fx of 2 is p square. So if I simplify this, I will get 8 times p to the power 5 times 1 minus p to the power, this is 3 and this is 4, 7.
Sir,
Hmm?
this is the way L function has been defined, right?
This is we defined it as
Like this.
product of
All
the PMF
density,
if it
all
is
density function, all density function.
yeah, all the density function of this particular sampling.
Sampling, yes, sorry.
Okay. Yeah. So this is if it is binomial, this will be the likelihood function. So this is how you compute the likelihood function. We yet not arrived to maximum likelihood. We are just talking about the likelihood function. So this is what the likelihood function for this binomial 2p, where for this particular sampling, for this particular sampling 1 0 1 1 2 0. Okay, understood? If
Yes.
this is different, then this will change.
The function will change.
Yeah, this is not constant for all binomial, for all the binomial. Okay,
Sampling.
so this particular likelihood is dependent on the samples which we take for the instance. Okay, so that is why you can see L is actually a function of this x1 x2 xn. Like if you change x1 x2 xn, this particular function L likelihood function changes.
Sir, if I take a wordy conversion of the same question kind of thing, can I say that the likelihood of in a bowler's this one, first ball one run, next 0, next 1, next 2, and 0. This is the probability. I mean, what is the probability of this particular random chances kind of thing? The likelihood of the total.
Correct.
Can I take it like that, sir?
Yeah. So likelihood means the same thing. So what we did is here is, so chance of getting this particular order. So in order to get first one 1, second one 0, third one 1, fourth one 1, fifth one 2, and sixth one 0, these all are independent events, and we are just producting those independent events because for an independent event probability will be, so consider this as an event. So 6 events and all the 6 events are independent. So if you want to compute the probability, it will be the product of each of the events.
But so why we given the likelihood name actually? Like it's a simple like we can consider like a normal probability. Okay, these are the independent events, and what is the probability? This is how we calculate, right? So why me? I want to ask this in the real time scenario also. Suppose something happens. Okay, something comes. So why do we put this likelihood function over there, sir?
because
It should be
my
coming
sense
in the
is
same sequence, sir.
huh,
In any game, actually, the sequence is 1-0-1-1-2-0. In an entire game kind of thing, it is very, very less likelihood.
less likely. See, likelihood is actually, we are actually estimating things, right? We cannot predict exact things every time. So this is my understanding of why we kept likelihood. Even I'm not sure about this. I have to go and like I have to do some searching on this. So why this likelihood term came actually?
So may I say something?
Hmm.
Yeah, it may look trivial, but the other name of probability is likelihood. Very loosely, we call probability as likelihood also. Very loosely. I'm not
Okay.
saying there is a firm definition.
So can we proceed?
What
sir?
is loosely?
Loosely means in a very vague
Raw
or very
manner.
informal
Correct.
way.
Yeah. Oh,
Sir, hello.
Likelihood means likely chance of occurring and
Yes.
yeah.
Hello.
Hmm.
Sir, if we only have samples, how do we know beforehand that the samples is following certain distributions?
No, we have taken some sampling, right?
Right, but if only we have samples on our hand, then we are calculating the likelihood using sum of distribution, means now binomial. How do we know beforehand that this
No.
distribution might be binomial?
If we know these are the methods we have to follow. If we don't know, you have to watch week 10 lectures. Okay. There our P is actually random variable. Okay, we don't know the distribution also. So in real life also we see, right, in the data you don't know directly that particular data actually follows some distribution. If you know that, why we study all these things? Okay, so we are going step by step. If you know the distribution, and if you know out of the distribution, if you don't know the parameter, actually if you don't know what the mean is, but you randomly taken one sampling out of it, and using that sampling we actually estimate the parameter, here it is like probability.
Yes.
Success probability we are computing. So we are estimating the success probability by seeing one instance. So maybe you say you are throwing a die. So how do you know that it is a fair die and having probability 1/6 directly without even how do you say that it follows an uniform distribution well ahead? So that how do you know? Do you know why how 1/6 came?
Observation.
So we call it as prior posterior. So we estimate that it follows one distribution, and we randomly do one experiment, and out of that experiment result we actually compute the posterior parameters, and from there by repeating the experiments again and again, we actually come to best estimation value 1/6. Okay, so we will study these things step by step. Okay, right now we are in the stage of we know the distribution, but we don't know the parameter of the distribution. But what we are assuming that is the parameter is actually a constant value, and one sampling out of it. Using that sampling, we are trying to estimate the given parameter. So there are two estimators. One is method of moment estimator, and another one is maximum likelihood estimator. So each of them has different steps. Now we are looking at how to estimate a parameter using maximum likelihood. Okay. Yeah. So this is the likelihood function. And what is maximum likelihood means? So as we studied likelihood just now, if you maximize this likelihood function, that is what maximum likelihood means. And my question is, why maximize? Why are we maximizing this likelihood?
To know best of the best chances. Sir.
Yeah, it's the highest probability. Yeah.
Highest?
Like to get this, to achieve something, like what is the highest probability? Like, I mean, on which value will get the highest, the value of particular function or whatever we're trying to do actually.
Okay, I can halfway agree to it. See here in this case, why we maximize these things, because here you can see this particular likelihood is a function of parameter. It will turn out to be a function of a parameter, right? This particular p is the parameter, and it will be like a function of parameter. So when you have the function of the parameter, why we are when we maximize this likelihood, what are we actually achieving? We are actually achieving the maximum for this particular maximum value, 8 times p to the power 5 times 1 minus p to the power 7. We are trying to maximize this thing because the maximum will impact this likelihood. So there will be a maximum likelihood chance of getting 1 0 1 1 2 0. So for that particular parameter, out of all the parameters, so you have different values to this p. So if you take this as a function, p can take any value in between anything. So out of all those different possible values the parameter take, which particular parameter value will give us the maximum value for this likelihood. Why maximum is what? Because if we get the maximum value, there is a high likelihood chance of trusting, or what we say, by taking this particular sample, taking that particular parameter, we say with maximum chances, we say p can take that particular value. So out of all the parameters, which parameter will give us the maximum likelihood? That parameter which we are going to find. So in order to find that particular parameter, we have to maximize this likelihood. Okay, how do we maximize this? So the maximum likelihood estimator is nothing but it is written like this: theta 1 star comma theta 2 star. So what we are actually finding is we are maximizing the x value. So whatever the parameters we have, so here it is p, but let's go back, just go back. So here we have taken parameters as theta 1, theta 2 like this. So what we are trying to maximize is we are trying to maximize the parameter. So parameters are theta 1, theta 2. So theta 1 star, theta 2 star are the maximum likelihood parameters. How we can find them is, you have the likelihood with us, and which is a function of parameters, which will be a function of parameters, correct? So we will maximize this with respect to the parameters. So we will get maximum value. What is this arguments? We have this arg here.
Argument.
Yeah, what does argument means in this thing?
So value of theta?
It's the value at which it takes the maximum.
Value.
Correct. In the lecture also it is
said,
right? So if you have the likelihood function like this,
yes, sir.
Somewhat like this. So this particular thing, this is the maximum value, and this is the argument. So at which the maximum value has occurred. So this L of 101120 is the maximum value we are going to get for some p, which is the argument of this max of theta 1, theta 2, pi of fx, this thing. So here p is the argument. L of 101120 is the maximum value. I hope you understand. This is like x and this is like y. We are maximizing y with respect to x, and we want x value.
Value of the function is y.
Value of the
function is y.
Value of the function is y. Correct. What we want is we want x here. So at which x actually the function takes the maximum value. Okay. So those are parameters to us. So now some examples. Let me start with basic examples. like Bernoulli only. Okay, so Bernoulli P. So first and foremost thing is just write what is the density function. What is the PMF here? So fx of x will be P when x is equals to 1, 1 minus P when x is 0. Correct? Now let us say we have x1, x2 and so on xn. This is the one, when I write small x, it represents one particular instance or one sampling. So for this particular sampling, if I write the likelihood function, this will be x1 gamma x2 and so on xn, which is the product of all the PMFs. Okay, so this will be like this, and this is like fx of x1 times fx of x2 and so on till fx of xn. Now see, x can take only 1 and 0 values. Let us say out of these n particular samples, we say we got k ones and n minus k are zeros. So if k samples are ones, then definitely n minus k samples will be zeros. Now if it is like that, so this product will be, if you understand correctly, this product will be n minus k zeros. So it's actually the product of some k p's. So there will be p, some one will be p, one other one will be p, another one will be minus 1 minus p and 1 minus p, like this. So but you know that out of these p's and 1 minus p's, there are exactly k p's and n minus k 1 minus p's, right?
True, sir.
Then I can write it like p power k into 1 minus p whole power n minus k. So this will be the likelihood function. Okay, now you can see here there is no x small x1, it is independent of the instant sampling. Okay, now it is a function of the parameter p. This is L. Now we have to maximize L. So in order to maximize L, if you have any function f of x, in order to maximize this f of x, what we will do?
Derivate to zero, or differentiate to 0.
Derivate it or differentiate it. So what we do is df x by dx is equals to 0. Correct? So this is what we do. You might have studied in Max 1. No?
Yes. That's one, sir. I am relating the same thing what Usha madam taught us.
Which are?
No, the above step, sir. Sorry.
This above statement?
Above step, if I take the likelihood of L1, L2, L3 in a continuous manner, all ones are independent kind of thing, so I can multiply to get the probability.
What is L1, L2, L3?
No, sir. I think he misinterpreted like how to get the independent probability, sir.
No, I'm clear, sir.
Actually, sir is asking like why do we differentiate to 0? That is his question, sir.
His question is why we differentiate.
Sir, this is what you asked, sir. But
yeah,
he's answering why do we multiply the different probability fx1 dot fx2 like that. I think he's answering that thing.
Correct.
Why we are multiplying? No, you refer to something like L1, L2, L3.
If we take.
Okay, what is L? Just define what is L1 here.
The likelihood 1, 2, likelihood 2, likelihood 3 kind of thing.
Why are we taking those many likelihoods? No, right? That is not what we are discussing. We take only one likelihood, that likelihood comes from this one sampling. We don't know the other we don't even know what other sampling results are. We did only one sampling and we have taken n samples out of it. We have taken this x1 is the first sample, x2 is the second sample, xn is the last sample, nth sample. And with respect to this particular one instance, we are computing the likelihood function. There is no L1, L2, L3, 3 likelihoods or 4 likelihoods. There is only one likelihood for one particular instance, and we don't even consider the second instance or second sampling and take the second likelihood. There is nothing like that.
That's what earlier what you have discussed, like I mean 8 into p to the power of 5 kind of thing is there, answer. Like that, actually some other functions will be there. Function 1, function 2, function 3 kind of thing. Those are different likelihoods only, sir.
Okay, will be there. So okay, now ask me your question.
No, I'm not asking anything, sir. I'm just relating to what
okay.
I have learned in stat 1.
Okay, fine. So we know this. How many of you know this actually? In order to maximize a function, we have to differentiate the function and equate it to 0 and find the x's. And at those
x's, sir, we know in maths we done same.
Yeah, in maths
like
we done,
math
right?
too, yeah, it was there.
Yeah, so either it will be minimum or maximum. In this particular course, we don't worry about minimum maximum thing. Every time it will be maximum only. You don't need to check for the second derivative. Okay. So what we have to do is, in order to maximize this function, any function, we differentiate the function and equate it to 0. Here also we do the same thing. You differentiate the function with respect to p. So this will be like product of 2. So again, in the lecture, professor has discussed, either you differentiate L and equate it to 0, or you take log L. So both you can do. Okay.
But so ultimately, after taking log L also, we have to differentiate that, no?
You have to differentiate that. Both the cases, you take L as the function or log L as the function. Okay, nothing changes because log L is an increasing function. So whatever the properties L will have, log L will also have the same properties. Okay, so you can do that, or else you can directly differentiate it. So this will be p power k 1 minus p whole n minus k divided by dp. So this is one function, this is another function. This will be like product of two functions, fg dfg by dx. So this will be f dash g plus g dash f. This also you know, right? Product rule of differentiation. So this will be like k times p to the power k minus 1 times 1 minus p power n minus k plus p power k times n minus k into 1 minus p whole power n minus k minus 1. Now this we have to equate it to 0. So if you equate it, you can take
it will be minus 1, no, sir. Then we'll have to differentiate 1 minus p also, sir.
Yeah, we have to differentiate 1 minus p and it will be minus 1.
Minus 1.
Correct.
Yes.
Correct. So this will be like p to the power k minus 1 times 1 minus p whole to the power n minus k minus 1. If you take it common, k times 1 minus p plus n minus k times p. Sorry, this will be minus. So this minus you multiply it here. This will be equal to 0. So this is not equal to 0 and this is not equal to 0 because P is not equal to 0 and P is not equal to 1. So this won't be 0. So this should be equal to 0. So from here we get K times 1 minus P minus N minus K times P is equals to 0. This will be K minus KP minus NP plus KP is equals to 0. This and this will get cancelled. From here what we get is P is equals to K by N. So just go back 2 lines. Here K represents ones, number of ones. So this is actually number of ones divided by N. And also some intuition, we can actually say x1 plus x2 plus x3 and so on xn divided by n, because x1 takes either 1 or 0 and there are k ones. So if you sum all these things, you will get k. So that will be equal to x1 plus x2 plus x3 plus and so on xn by n. Therefore finally what we have to do is, the last step is, once you get P, now here it will be small p, you can write it as P star ml will be x1 plus x2. So small x you will replace it with capital X, xn divided by n. So this is the maximum likelihood estimate of Bernoulli. So this is actually equal to method of moments estimator, correct? Even for method of moments estimator, for Bernoulli it will be x1 plus
same expression was correct.
Same expression. So for Bernoulli, even if you choose maximum likelihood estimator or method of moments estimator, it will be same.
Sir? Now that question becomes valid. Like say for example, if I take my second sampling, right? So my P star will vary. If I take my third sampling, then again I will get different P star, right? Correct, na?
See, ultimately you are going to get, see, whatever the sample you take,
that instance sampling, what you are calling
that
instance.
Yes, but that particular instance.
So if I take my second instance sampling, so I will get a different value of P star, this is my estimator. I will get a different value for estimator, right?
No. In this particular case, you won't get. That is what I just said, right? This particular x1, x2, xn will not appear anywhere.
No, not in this particular case. If I take second instance sampling, like again I collect 10 samples, right?
Okay.
So in that case, maybe that I am getting only 3 ones and 7 0, right?
Okay.
If I take my third sampling, I am getting 4 ones and 6 0.
Okay.
Like that I am saying.
Like that you are saying, I am agreeing that. See, here small x1 is the first sample in first instance.
Yes.
Okay.
Yes.
Are you able to see that small x1 somewhere in our computations?
No,
nowhere, right? That means whatever x1 is independent of what we computed.
That's towards the end. I am writing the x1 plus x1, x2 plus x3 up to xn divided by n. Here again it is appearing. Here again it is appearing.
Here it is appearing as a sum, right?
Right. So say for example, if I second, this is my first instance, right?
Okay.
In this case, I am getting 4160. So yes, 4160. So my answer is 4 by 10, right?
Right.
In my second case, I am getting 5150. So my answer will be 5 by 10. In my third instance, I am getting 3170. So my answer will be 0.3. So I am getting different estimate. That's what my point is.
Yeah. Depending upon the correct sampling, you will get the different value.
Value of estimator.
Value of the estimator varies.
Yes.
That is why this is a random variable actually. Okay. Right. This is not a constant. This is a random variable. Okay. This will also vary.
So down the line, are we going to discuss that which one to opt which one to select down the line, like in week 10 or week 11? Are we going to study that?
We are going to study. We are going to see.
Okay. 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 Okay, sir.
Yeah. Okay. Yeah. There are. Yeah.
Can we? Where you actually derive p is equal to k by n? Yeah. From there, how did we get to x1 plus x2 to xn by n?
How do we get is, see, you just see x1 plus x2 plus x3 and so on plus xn.
Yeah.
So in this, we said there are k ones and n minus k zeros.
Correct.
So if it is like that, what will be the sum be?
Sum is going to be k1, k basically.
K.
Yeah.
That is what we replaced with. We replaced k with the sum actually.
Oh, okay. 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 All right. Thank you.
Okay. So this is how we can compute. There are even professor has computed many.
Are you going to take one more example, sir?
Do I have to?
Uniform 0 theta, sir. Professor has done this calculation, but bit
Okay. Okay. Now these are the steps. These are the steps you have to follow for any distribution.
Yes, sir.
So what we actually did is, I will just quickly refresh. What we actually did is, whatever the instance or sampling, we just took one sampling out of it, out of the distribution, and we found the likelihood function, which is the product of the density function. And that likelihood function will be a function of a parameter. If it is single parameter, it will be the function of one single parameter. If it has two parameters, that will be a function of two parameters, this likelihood function. So once you have the likelihood function, we have to find the maximum likelihood of this. So what we do is we differentiate this this function L with respect to P and equate it to 0. By equating it to 0, we find the value of the parameter, and that particular parameter value will be in terms of n or whatever the values we know. And final step is, after you compute this, for this particular P, this particular dl by dp will be 0, and that particular P, this particular likelihood function will be maximum. So this P will be the maximum likelihood estimator. So in the last step, what we do is we replace this P with P star ML and small x's with capital X, and that will be the maximum likelihood estimator. Okay. Same thing you have to do for other examples, like if it is exponential lambda, if it is Poisson lambda, if it is geometric P. Okay. So for all this, I guess for most of them it will be same as, so here it will be MME, same as MMEs only. All these three cases same as MMEs only. Okay. So for this,
one rather probably not important question, but why do you call it MME when it is maximum likelihood estimator? MLE shouldn't it be?
MLE.
No, you put it as MME over there.
That is the
MME is method of moments estimator.
Okay. Sorry.
So this is MME, method of moments estimator.
Okay.
Okay. So this will be exponential lambda. For exponential lambda, it will be something like n by x1. For this will be the same, I guess, x1 plus x2 plus and so on xn. Correct? Correct? Wrong?
Yes, sir. Yes, sir. Correct.
And for final one, it will be p hat of ML will be geometric P. So what will we get? You can actually find this. Did professor do this thing?
No.
No? Okay, we will do it then. Okay, let me take this one example. So x is geometric p. So first and foremost thing is write fx of x. So this will be 1 minus p to the power k minus 1 times p for x is equals to k. Correct? And x can take values from 1, 2 and so on. Now we have x1, x2 and so on xn. Likelihood, write the likelihood. So this will be the product of y is equals to 1 to n. Okay. So this will be okay. This will be slightly difficult, I hope. So this is something like fx of xi. And if we know exactly these xi's, then we can estimate, I guess. Okay. So let us take exact values then. 1, 3, 5, 4. Okay. So we have taken 4 samples. If it is like this, then this will be fx of 1 times fx of 3 times fx of 5 times fx of 4. So fx of 1 is
P.
Fx of 3 will be 1 minus p whole square times p. So 2 failures and a success. Third time success. And fx of 5 is 1 minus p whole power 4 times p. And this will be
1 minus p to the power 3 is p.
1 minus p to the power
3
to the times p. So this will be like 1 minus p whole to the power 7, 8, 9 times p power 4. P4. Okay. Okay. Like this. Now this is the likelihood estimate. I think we can generalize this also. Looks like we can generalize. No need to do. So we have x1, x2, x3 and so on xn. So this will be like 1 minus p whole power x1 minus 1 times p, x2 minus 1 times p, x3 minus 1 times p, like this, and so on xn minus 1 times p. So this will be somewhat like, there will be p to the power n, and this will be 1 minus p whole power x1 plus x2 plus and so on xn minus n. Okay, this is the maximum likelihood function. Now what we have to do, we have to maximize this. So in order to maximize this, dl by dp will be the same thing, n times p to the power n minus 1 into 1 minus p whole power x1 plus x2 plus x so on xn minus n.
Can we take that one as also a number, sir? Because finally it reduces to constant, right? X1 plus x2 plus x3.
Already?
No. X1 plus x2 plus x3, in a case kind of thing, it will be reducing to a single number, right, sir?
Can you be louder? I'm getting somewhat background disturbance.
The x1, x2, and all like that will be completely, adding up to a single number.
Single number, correct.
Can we take some delta or something like that, sir? Any other?
You can
variable.
take, but we want in terms of x1, x2, xn, right?
In differentiation, it will be easier. That's all.
In differentiation, okay. Thanks. So if you differentiate this also, it will be like first term differentiated with the next term, and this will be minus p to the power n, and this will be some, yeah, the summation xi minus n times 1 minus p whole to the power that summation minus 1. That particular summation xi minus n minus 1. Okay, if you do it like this and equate it to 0, so what I can do is I can take p to the power n minus 1 common from both the terms, as well as this 1 minus p whole power this thing common, and I will be remained with n times 1 minus p, only 1 minus p will be remained here, minus p times this summation xi minus n will be equal to 0. So from here we get n minus np minus p times, so this will be x1 plus x2 and so on xn plus np is equals to 0. This and this will get cancelled. So from here we get p is equals to n by x1 plus x2 and so on plus xn. So this is what we will get for geometric. And is this the same MME?
The factor which you taken common, that you have cancelled it out, right?
That we will get, that will automatically get cancelled out because p will not be 0 and 1 minus p will not be 0.
Correct.
So this will be the same MME, I guess. For MME also you will get the same thing, if I am not wrong. So have someone computed this p using method of moments estimator for geometric? No, is it? Okay, what will be the expected value of geometric p? Everyone left or?
1 by p, right, sir?
Correct. No one? Am I audible?
Yes, sir, 1 by p.
Yeah, 1 by p is correct, but no one is answering. Okay, 1 by p.
This is derivation, sir.
From here you can get, right, m1 is equals to 1 by p, p is equals to 1 by m1, and here itself you will get n by p hat of MME. So x1.
How for geometry p
How this is 1 by p?
Sir, by method of moment.
By method of
moment. You are computing this by the method of moment.
I just computed. See, my first question is: have any one of you computed, estimated the parameter using method of moment for geometric p? No one answered.
Yes, sir.
Then I asked the second question: what is the expected value of geometric p?
Okay, sir.
Then only one of you responded with 1 by p. Later, two other synced with that Kavita. So they said 1 by p. So from there, I computed method of moments estimator. Okay.
Yeah. Yes, sir.
Okay. Now the method of moments estimator and the ML estimator both are same.
Same. Yeah.
Okay. The change will come when we talk about uniform distribution. Okay.
Zero theta continuous.
Discrete one.
No, zero theta continuous.
Sir,
Zero theta
continuous or discrete, sir?
Continuous
Sir,
and
can you
discrete.
take discrete one first, sir?
So yeah, can you please do it for give an example for discrete one, because I'm facing problem in the activity question in that thing. Discrete uniform.
Discrete uniform.
Yeah, I mean it might be basic problem might be. I mean I'm getting stuck at something which may be very silly, but I'm not understanding it. That is
I too have doubt
9.6
in that question,
yeah.
sir.
See, I think most of you have that doubt.
Yes, sir.
So it is taken from some IID uniform. Let's say from 1 to some k. Okay. So what if this is used by method of moments?
Sir, if I am doing this by maximum likelihood estimator, I am getting 1 upon, so the probability of each of the outcome is 1 upon k in this.
Right.
So yeah, so if I multiply all of them.
Okay.
Yes, sir.
Correct. Whatever you are saying is correct. Okay, let us consider one sample.
Okay.
One sampling or one instance of the samples and samples. Okay. And you see whatever the x1, x2, xn are, this particular k should be greater than these values. If it is lesser than that, I cannot have my sample which has outside k, right? Whatever the samples I take, those are all less than k.
Okay.
Yeah.
Correct?
Yes, sir. Less than k.
This x1 comes in from 1 to k, not more than k.
Okay.
And also this x2 comes from 1 to k only, not more than k. Likewise, all the last sample also xn will also lie in between 1 to k, not more.
Yes, sir.
That means whatever the maximum of these x1 to xn, my k should be greater than the maximum value also.
Yeah.
Max of x1, x2 and
Sir,
so on, xn.
Sir, suppose if xn becomes equal to k, then
Even then, yeah, greater than or equal
Greater
to.
than or equal to, yeah.
Okay.
Okay.
Okay, convinced with this?
Yes, sir.
Yes, sir.
Now, what will be the likelihood?
No, I didn't get it.
This is product of I equals to 1 to n. So
the
each of them
uniform-
will have probability 1 by k.
1 by k, yeah.
Sorry, sir, I didn't get one thing, sir. So 1 to k, what the discrete values, uniform one question.
Uniform 1 to k with uniform 1 to k means each of the value has equal probability of occurrence with probability 1 by k.
The 1 to k, see, sequentially the values are 1 to k.
Sequentially?
1 to k, right? 1, 2, 3.
1 to k, any number has equal chance.
Okay, 1 by k is the probability.
With probability 1 by k.
Okay. So here k greater than or equal to max, I didn't get that, sir.
K greater than or equal to max. See, this particular is a one instance of n samples.
Yes.
So whatever the samples I get output, those all are in between 1 to k, not more than k.
Yes.
So if I am looking at uniform 1 to 10 and I am taking samples out of uniform 1 to 10, I cannot get 11 or 12 as my sample.
Yes.
Right? So these all should be less than or equal to k.
Yes.
So even the max, if I just look at the maximum of these things, that particular maximum also should be less than or equal to k. So that is why k should be greater than or equal to max of this. And this particular product we have fx of xi's. And this is every xi, the PMF of every xi will be 1 by k. So this will be 1 by k to the power n. Okay.
Right. Yeah.
Now we have to find the maximum value of k.
Yes.
Correct. So not the maximum
Sir,
value of k, the value of k for which this particular 1 by k to the power n
likelihood is maximum.
Maximum.
Oh, I took it as 1 by n raised to n, so I got confused.
Sir, could you please repeat the statement, sir?
Okay.
Repeat how it is 1 by k to the power n.
How it is 1 by k to the power n. Okay. So this is actually fx of x1, fx of x2, and so on, fx of xn. So fx of x is actually, this is uniform 1 to k, right? So fx of x will be 1 by k when x is in between 1 to k and 0 otherwise. Okay, this will be the density function, PMF actually, PMF. So fx of x1 or x2 or x3 or xn, everything will be 1 by k. So this is the product of 1 by k times 1 by k times and so on times 1 by k, n times. So therefore it will be 1 by k to the power n. So now what we have to do is, we have to find k for which L of x1, x2, xn is maximum. Okay, so this is a decreasing function, correct?
Right.
Yes, sir.
As k increases, this value decreases, correct?
Right.
So you see,
Sir,
we need the least possible value of k, for which for that particular least possible value of k, we can get the maximum likelihood.
Yeah.
Sir, it is driven by both k and n, is it?
Sir.
See, n is not, okay, n is not a variable here, n is actually fixed. Okay, the only variable we have is k.
No, but
so that is the problem actually. We don't understand what should we take as a variable. That's the problem.
Parameter is the variable, right?
Okay.
What is the parameter here? Is it k or n? N is number of samples we took.
Okay. Got it. Okay.
So it can be any one of the values from 1 to k, right?
Which one?
Each one of x1 to xn is going to be between 1 to k.
Between 1 to k.
Yes,
between 1 to k, not more than k.
Not more than
yes.
Sir, one basic query here, sir. You said that k is a variable, right? And n is the sample. Now my query is, like in a particular set, x can take finite number of values. So according to me, k should be fixed and sample should be variable, because I don't know how many things will be in the sample, elements will be in the sample, right? How can k be variable over here?
How can, we don't know the parameter of the distribution. Okay,
Can I take a small intervention over here, sir?
See, okay.
Let us say 1 to k. The n number of things are the only problem, sir. So if you take all these ones are lottery tickets kind of thing. In a simple example,
See, there is a bin. Okay. So this is a closed on top, and you don't know what numbers are there inside. So there are some balls, and each ball is given numbers from 1, 2, 3, 4, 5, 6, 7, and you don't know how many balls are there in this bin. Okay, you don't know. This is closed, and you are allowed only one hand can go inside and pick out one ball outside. Okay, what we are actually doing is, we wanted to take 10 balls by repetition. Okay, you just put your hand inside, you just take out one ball randomly outside,
right?
Okay, and you just saw the number.
Will be the number of the ball that comes out.
You don't know the number of balls inside this.
Okay, got it.
N you can fix. Okay, and the number of samples, number of times you pick ball is in your hands. Okay, and the number of balls is not in your hand. You have to estimate how many number of balls are there in the.
I got it. Yeah.
You are playing a game, maybe So you will win if you guess
N
very
is
near.
less than or equal to K. N is less than or equal to K.
What is no need, right?
No, N can max it can go to K. Say K is the number of balls inside.
We are not pulling out one ball and we are not keeping it outside. We are actually pulling a ball outside and seeing the number, noting it down, and we are keeping again the ball inside.
With replacement. Okay.
With replacement. We are doing with replacements.
Then only the experiment is what we say independent to each other, right? If I remove one ball for the first sample, for the next sampling, the distribution changes. You remove one ball outside of it.
Yes.
Okay. So we are taking one ball, seeing the number, and we are throwing the ball again. We are mixing something, we are doing something, and we again put our hand inside, take one ball outside, and we note down another number. Like this, number of times you do this is in our hand, and you have to estimate how many number of balls are there in the bin. So which one will be the parameter here?
K7 here.
Number of balls in the bin, yeah.
Not only 7, there are many.
K is parameter.
K is parameter.
Right.
N is
number of samples which we are doing.
Okay. Yeah.
Okay, got it. Yeah.
And this function, likelihood function, is a function of parameter. So K is the parameter, and it is like 1 by K to the power N. So what we have to do, we have to find the value of K. For what value of K, this particular likelihood is maximum. So we know that this is a decreasing function, and if we take larger values of K, big values of K, this likelihood function takes values lesser and lesser.
Minimum value.
Right.
Yeah.
Right.
So what we have to take is, we have to take the minimum value of possible value of K in order to have maximum likelihood.
Right.
And we know that K is greater than or equal to max of this. So for this minimum of all the possible values of K, what will be the minimum?
Maximum of X.
Yeah.
X. Yeah.
So this is an lower bound here. So there is a lower bound here.
So this is confusing.
So actually, this is very confusing.
Sir, when we
parameter
say
is 1 by K, na, sir?
Sir, just for a second, sir, can I just want to clarify on one thing?
Yeah.
Hello?
Yeah.
Yes, sir. See, if we are considering this experiment, like we are pulling out one ball, so K is the face value of the ball, right? Let's say you're numbering from 1 to, let's say there are 10 balls or 20 balls.
No. This X1, X2, Xn are the face values.
Okay.
So X1 is the first ball face value.
Okay.
X2 is the second ball face value. Second time you pull out a ball, whatever the number comes on it, that is the X2.
So yeah, sir. So balls are anyway numbering from 1 to some value, right? 1 to K, right?
1 to K, yeah.
So when I'm pulling it out, I will not get anything more than K, right?
Anything more than K, correct.
But can I get all these n values as the same value? Like if it happens that unlikely even that you are getting the same ball every time.
It may. In your instance, if it is that the case, then you say in your ball you have only one ball, and if you can see the number is something like 8.
So because the thing which is confusing is K for the maximum likelihood 1 by K power N. So K must be minimum. So this K minimum is how to get this K minimum? That's confusing.
See,
K should be minimum, right? For 1 by K power N to be maximum.
We are trying to maximize this thing.
Yes, sir.
1 by K to the power N should go to maximum value. So you draw the graph of 1 by K to the power N. So something like 1 by X to the power N. How will be the graph of this be?
It will be tapping down towards x-axis.
As X increases, it will come approach to
down.
0.
Yes, sir.
Correct?
Yes,
as we increase X, it will come down to 0. So in order to have the maximum value, what we should pick? We should pick the least minimum possible value of X.
Yes.
Correct?
Yes.
That is what. So you have to pick the least possible value for K.
So how to get that?
How to get that? So we know that max of X1, X2, and so on xn is less than or equal to k. So k is always greater than or equal to this particular value, max of x1, x2, so on xn. Out of these all possible values, what will be the minimum?
Minimum of x1, x2. Okay.
No. See, let's say max of x1, x2, xn is this. This is one value actually. Okay, maximum value of out of all these n samples, what is the maximum value? So if I have samples like 1, 3, so let us take this bin itself, 1, 3, 5, 7, 9, 10, 2, 1, 5. Okay, this is how the.
So
whenever
I will take one.
You will take
one. No? So in the case of one, the value of function will be maximum.
No. You have to take max of all these values.
Yeah.
Consider what is
That
the max
will be
of,
the minimum value of k.
what is the max of all these values?
10.
10. So
Yeah.
10. So k should be greater than or equal to 10. Correct? So
Yes.
if you are seeing 10, once you draw the ball and if you have seen 10 on that particular ball, number 10 on that particular ball, you are guaranteed that the number of balls inside the bin is actually greater than or equal to 10, not less than that. Correct? If I can see 10 numbered ball, that means I am guaranteed that there is 9 numbered ball, 8 numbered ball, and so on till 1 numbered ball.
Sir, can we complete the equation? So 1 by k to the power n. So now if I write 1 by 10 to the power n, right? Can we complete the equation? Yes. So now it will be 1 by 10 to the power n, right?
1 by?
If I am taking k as 10, right? To maximize this function.
So k as 10. So k can take values 10, 11, 12, 13 and so on.
But here I'm having the maybe very silly doubt. If I am putting 1 by 10 to the power n, say for example n is 100, right? Or n is 20, right? So 1 by, if I am taking k as 1, so that is giving me the maximum value, not the 1 by 10 to the power n is giving me the maximum value.
Ganga Prasad, you have to understand one thing. If you are giving k value as 1, then that means you are saying that you don't have any, your samples doesn't have any number greater than 1. Right? So if you say k taking value 1, that means you are saying that it is uniform and takes value only 1. Your sample doesn't say that, right? What your sample says is, your sample values are actually given that 1, 3, 5, 7, 9, 10, 2, 1, 5. So these are the sample values you have. And now by looking at these samples, what I can guarantee is my k is always greater than or equal to 10, not less than that.
Okay.
Correct or not?
Yes.
How I am guaranteeing that? I am looking at the maximum of these all samples, and I am making sure that whatever the maximum is, my k value is greater than or equal to that particular maximum value. Okay. Now my k is, so that is what I am.
But why are we defining it such a way, sir? K should be maximum, greater than the maximum or equal to the maximum.
Why it's not we defining, it's the intuition we have. Okay, so see here, that is what you have drawn balls. Let us take this example only. First ball has number 1. Again you throw that ball 1 inside and you mixed it, and next time you pick ball 3.
Yes.
So once you are picking ball 3, now what you know that there is ball 2 also inside it.
Yes, sir.
Because ball 3, I have seen ball number 3. So that means there is ball number 2. There won't be ball 3 numbered without having ball 2.
Yes.
So now what is my guarantee? I can guarantee that there are 3 balls inside it if I see 3.
Yes.
Next time I have seen 5. Now what can I guarantee?
Yes, sir. 5 and you definitely will have 4, 3 and 1.
4, 3, 2, 1. Likewise, I have seen 7, 9 and 10. 10 also I have seen. Now I have seen 10 numbered ball means what I can guarantee? I can guarantee that there are at least 10 balls inside the bin.
Yes.
At least 10 balls inside the bin. At least 10 balls means our K is actually greater than or equals to 10. The number of balls inside is actually greater than or equals to 10. Correct?
But it can be let us say if we have random like balls like numbered 1, 3, 5 and 10.
No, that is not the experiment we have. See, we said uniform. Okay, if you are confused with bins, let us say lottery tickets. Okay.
No, sir, that will be a wrong example. I tried that one. No replacement is there in the lottery ticket.
No replacement will be there. Okay. So you see here only, you try to understand. Okay. We numbered each and every ball with starting from 1. So 1, 2, 3, 4, 5. See this uniform. We are trying to create an example for this uniform 1 to K.
Yes,
so we don't know K, what K is. So each 1, 2, 3, 4, each of the number represents one ball.
Yes.
Okay. And picking one ball out of that bin has equal chance. Okay. Even if you pick 3 or even if you pick 1 or even if you pick any ball, picking any ball has equal probability.
Yes.
Okay. Now, for the first time I picked the ball, I have seen number 10. Let us say I have seen ball number 10.
Yes.
What I can guarantee from that ball number 10?
Minimum 10 balls are there in the
minimum 10 balls are there inside the bin, right? See, if I see number 10 inside my bin, that means now only I said we started from 1.
So, but
and
if we are, sorry, but if we are saying that the distribution is x1 to xn, but the values will be from 1 to k. So it could be that 10 could be also the maximum, like k could be the maximum value, right? Like in the sense, if I get 10,
could be the maximum value.
10 take
Yeah, k
10 could be maximum. So the other values could be 10 or less than 10. No, not 10 or more than 10.
Why less than 10? Whatever sample we have, we maybe 11 inside the bin, but you might not have taken it out, right? See, even 11 numbered ball may be inside your bin, but you haven't pulled out the ball 11.
Okay, I got it. So which means that 1 to k is something which would likely to be more than sequentially if you arrange 1 to k, it would be more than x1 to xn, right?
More than all the x1 and x2. So
Yes,
more than the maximum. If I look at the maximum of all the samples, if my my k will be more than that maximum value or it will be equal to that maximum value. We cannot say. Either it will be equal or it will be greater than that maximum of x1 to xn. Okay. Out of these all possible values, so this particular thing is actually, let's say, x. So kth sample has taken the maximum value. Sorry, k, let us not repeat. X star maybe. So there is something x star among these x1, x2, xn. So xp maybe. Okay. 1, 2, n. There is some xp which takes the maximum value. So if this will be the xp and k can take all the values greater than or equal to xp. So out of these all possible values, what is the minimum possible value for k? xp. So k should be equal to max of, so k hat or k hat ml. We have max of x1, x2 and so on xn, capital X. So this will be the maximum likelihood estimate of uniform discrete case. Okay, this is different from, this is not equal to
MME.
So MME, this is very easy. Okay, MME, I guess you will get something 2 times of something, right?
Yes, 2 times.
2 times x1 plus x2 and so on xn by n minus 1 or something like that. Okay. So ultimately the end result, if you don't understand whatever the half an hour before has happened, ultimately end result is more important. Okay. So end result, what it says is, if it is uniform 1 to k, and if you have a sample with you, max of sampling with you, max of whatever the samples you have observed, that will be the better estimate for value k. Now doubts. So uniform is also the same thing.
Uniform, we can take 0 theta. Or 0 k. Yeah, uniform, sir. Yes.
Uniform is also the same thing. See, nothing changes, right? Fx of x will be, if it is uniform 0 to theta, what will be fx of x? Density function.
Zero otherwise.
Right?
Yes.
The same 1 by theta, the same thing. K should be, this particular theta will be greater than or equals to max of whatever the samples we have observed. And out of these all possible values for theta, we have to pick the minimum, because the likelihood function will be 1 by theta power n.
Yes.
In order to L to be maximum, theta should be minimum possible value. The minimum possible value is max of x1, x2, and so on, etc. Okay. Whatever.
Sir, in this type of question, we cannot differentiate and equal to 0 to find the maximum, because
we cannot differentiate.
Yeah, I did that mistake. That's why I couldn't get the answer.
Yeah. So these are all the intuition.
So, but does that, I mean, just to understand it properly, I'm asking this. In a simple case, like there are suppose 1 to 10 number balls in a bin, and I don't know that. And is it like that 10 number ball will always have the highest possibility to be picked up? Is it that way?
No,
Do you mean to say?
No.
Then I'm not understanding it. Okay. K is max, right? So in that x1 to x10.
Review the video and just follow the search idea, ma'am. It will be easier. Within a couple of sentences, you can understand very easily and follow it.
Okay, fine.
So the parameter is not probability, it's the range.
It's because it's a sampling with replacement. The maximum could be 10. That's all. We cannot say that x1 will be 1 and x2 will be 2.
Okay, got it. Yeah.
Sir has lost the connection. Maintaining.
Yeah,
the
looks
trend.
like
Maintaining the trend. No, class is not over. Don't worry, he will come back.
Normally, it goes to 2 hours.
This happens only with sir's class. In other class, this never happens.
Generally, after 2 hours, he loses the connection. I think.
Yes,
he joins.
Yes.
Yeah.
He will. He will come back. Then he will request them to give access to him.
Hello. Am I audible?
Yes, sir. Welcome back.
We are waiting for you.
Yes, sir. We are waiting for you.
Yes, sir.
Okay, it's not like that. It's not
I got it, sir. The range basically, the number of balls.
Range.
Right?
Yeah, the number of balls.
Okay, got it.
And also we are just estimating these things. Okay, in this week we are just estimating our parameter. It's not the exact value for the distribution.
Right.
So in order to be for more less error and more precise, so we actually make it we actually predict it like this. So using these methods we actually predict it. Instead of going randomly, we predict it like that.
Yeah.
Okay. Okay. Now
excuse me, sir.
Yeah.
If our algorithm is like then we have two parameters, right?
Just a second, ma'am. Can you move your mic a little further from you? So I'm getting loud noise, and I'm not able to clearly hear you.
Hello.
Yeah. Hello.
If the uniform interval is like A, B, then two parameters are there, right?
Okay, if it is like uniform AB, then there will be two parameters.
Then we have to find minimum of if now the value of A, then we have to find the value of
Your voice is too blurry,
Your
ma'am.
voice is jarring.
Yeah. So maybe you are talking by keeping your mic very nearer.
Mic.
Huh?
She got to get a little away from the mic.
Yeah, you should go a little away from your mic.
Can you hear now?
Yeah.
If we want to find the value, estimate value of A, then we have to find the minimum of x1, x2, right?
Minimum of correct. So if it is x uniform in between A to some B, A plus 1, A plus 2 to B, if you want to estimate the value of A, then we know that whatever the samples you see, that will be so x1, x2 and so on xn. So minimum of this will be greater than or equals to A. So that from there we will get ultimately A should be equal to min of x1, x2 and so on xn. Okay, reverse tracing. So there we will look at the maximum, here it will be the minimum. Okay, now
can you please again sort of a high level summary on bias, error and all other connected things?
Bias, error and all, is it not discussed? I just wanted to take the activity questions of these 3 lectures which I discussed just now.
Yeah, in these activity questions I didn't see that bias, error related questions.
No, what am I saying is whatever the lectures just now I have explained, like 9.678. So what I thought is I just take the doubts of these 3 lectures. Are there any doubts first? Let me take those and we will go back.
So can you scroll up a bit, sir, just for a second, the earlier marking. Okay. Yeah, just yes, one second.
Or
no, just down. Yeah, this part. Yes, you can freeze now. Yes.
Okay. Okay, my question is, do any one of you, those who have solved 9.6, 9.7, 9.8, do you have any doubts in these 3 activity questions?
Sir, 9.64.
9.64 तो डिस्कस किया था ना हमने? No?
4 नहीं, 9.5 किया था.
9.5, okay, 9.6. Let me open that. Okay, 9.6, question number
4.
Suppose the lifetime of light bulbs is modeled by an exponential distribution with unknown parameter lambda. We test 5 bulbs and find that they have lifetime of 3, 4, 2, 5, 6. What is the maximum likelihood estimate for lambda. Okay. Have you done question number 3?
I think so. Just let me check. Number 3. No? Yeah, I have done that.
You have done that?
Yeah.
So what answer did you get?
Oh, just a second. I'll just 9.6. Hold on.
3.
Yeah, option 3 actually.
Option 3 you got. That is the likelihood function for lambda.
Yeah.
Okay. In order to find the maximum likelihood, what we have to do?
I have to differentiate and equate it to 0.
Differentiate it and equate it to 0 and find the lambda in terms of x1, x2, xn.
Right.
So, okay, what will be the maximum likelihood estimate for exponential function lambda?
N by x1 plus x2 plus x3.
So this was, I guess, this was discussed in lecture also.
N by x1 plus x2 plus x3.
Okay, if you done question number 3, from there I will take you. Okay.
Okay.
So we got L has likelihood function as lambda power n into e to the power minus lambda into x1 and so on xn. So this is what you got, right?
Yeah.
Now our next thing is dl by d lambda.
Right.
Right. And again 2 functions. So it will be easy if you take it like log.
Take a log, yeah, log.
Okay. If you understand log, let's go with log. So log L. So this log L will be
n log lambda.
N log lambda.
Minus lambda into x1
minus
to xn.
Lambda into
Log e.
x1 plus and so on xn.
That is 1.
Log
yeah.
e is
1, yeah.
Okay.
Yeah.
So this is what log L is. So if you differentiate with respect to lambda, what we get? N times log L differentiation.
1 by lambda. Yeah.
Okay. N by lambda minus here differentiation.
X1 plus up to xn, that's it.
Xn. We have to equate it to 0.
Yeah.
Yes.
Here lambda will be n by
What
x1.
did I do actually?
X.
Yes.
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 So this is the estimation. So what we have given you? We have given you the values of x1, x2,
n is equal to 5,
x3,
sir.
x4, x5.
I have to just input these values and okay.
Correct. So we have given x1, x2 to x5. What are those values? 3, 4, 2, 5, 6.
5 by 20.
3, 4, 2, 5, 6. So n is 5 and x1 is 3. So the lambda maximum likelihood of lambda is actually 5 by 3 plus 4 plus 2 plus 5 plus 6. Okay. So you compute the value and enter the answer.
Okay. Yeah.
That is how.
Your log is with this e.
Huh?
5 by 20 is 1 by 4. Is it 0.25? But the answer is 0.23.
5 by? This will be.
The answer is in range actually. So that's right.
Yeah, answer is in range. 0.23 to
So that is right.
Yeah.
I think I did a silly mistake in calculation again. So
how did we get the range here? We are getting a unique number 1 by 4. Is it 0.25? How do we get?
We took the log, sir. That's why the answers might be having a range kind of.
No, not at all.
Because the answer is in range 0.23 to 0.27.
Range only, right? What's wrong in there?
Yes, sir.
Do you want us to give exact 0.25? As it is non-integer value, we have given range.
Right.
Oh, okay. You are telling that you are accepting the answer anywhere between 0.23 to
0.23 to 0.27. Yes.
But how did you fix that range?
That is back-end work we do. We give some error.
Bias and error.
We use error and bias. We compute that and to give 0.2% error or 0.3% error. We use past students sample, and what we do is we use weak law of large numbers and compute the probability. No, we won't do any in those things.
All right. So we can simply give 0.25, but still we are within the range.
Yeah, you will be within the range.
Thanks, sir.
Okay. So any other doubts? 9.7, 9.8, or else those who are done today's, you can leave.
So I think I'm having doubts, but I'll go through them again. I think I may have done some mistakes and
maybe you just go back.
Yeah. You may ask, still we have time.
Okay, so those who have small doubts can stay back, and those who are done can leave. Okay.
Okay, sir. Thank you.
Yeah. Thanks a lot, and have
thank
a
you,
good
sir.
day. Yeah.
Have a good night. Thank you.
Yeah. Any small doubts, like 10 to 15 minutes of discussion, and we can wind up.
I think, sir, Mr. Mohan was asking about bias, variance, and relation. So I have also a doubt. Sir, am I audible?
Yeah.
Yeah. So I am also having a doubt related to that. I think there is an equation called trade-off, right? So there, sir has defined as risk equal to bias square plus variance, right? Risk. So can you explain this equation and from where this is coming, sir? Risk equal to bias square plus variance.
From where? Even I am not worried about.
So, but just can we prove something like this? Risk equal to bias square plus variance, because there are many numericals based on this formula.
Proof of this, is it?
No, not proof. Based on this formula, there are many numericals. So yes,
there are very many numericals in order to find the risk.
Yes. So how we are defining this relationship, like risk equal to bias square plus variance? Because individually their definitions are clear, sir. There is no problem.
Okay. So, but aren't we getting, if we expand and look at something like?
No, I could not achieve that, sir.
Okay, maybe